I hope to make or establish some new information on the bowline knot today, and it involves handedness. So I'm going to talk somewhat about handedness in the beginning and then go about explaining what I've discovered on the bowline. Most people can look at a hand and say that's a right hand. They also can look in the mirror at the right hand and say that's a left-handed. That's a left hand in the mirror because handed objects have mirror images, and the left hand is a mirror image of the right hand, and that characteristic is also exhibited by handed knots. So a lot of knots can be either left-handed or right-handed and are not interchangeable. Turns are the basic handed structure of knots. This is a single turn, and this is also a single turn, and they are not superimposable, but they are mirror images of each other. One is right-handed and one is left-handed. How do we determine if it's a right-handed single turn or a left-handed single turn? The right-hand rule establishes that if you are wrapping the thumb in the direction that the thumb is pointing, and the wraps are proceeding in the direction that the fingers are pointing, then that is a right hand wrap. So since this is a right hand and I'm wrapping in the direction of the fingers, these are right hand wraps, and this is a right-handed turn. And you can learn to recognize it when you look at the top of this turn where it's doubled. The one farthest away from you goes off to the right, but you use the thumb rule, the rule of thumb, to determine for sure if this is right-handed or left-handed. Now, we can form a right-handed turn and make a bowline knot. Go up and around, come back down. We have a bowline. You turn it over this way, you can see the right-handed turn is right here. That's a right-handed turn. And you'll notice these double ropes are on the right. Now, we can also do the opposite. We can make a left-handed turn and form a bowline knot. And we now have one that is started with a left-handed turn, and you'll notice the double ropes are on the left now. And these knots are mirror images of each other. So the question is, these appear to be chiral knots or knots that are handed. Then the question is, are they really handed knots or are they not? So there are knots that do not have handedness, and here is the figure of 8 knot. This is the simplest knot that does not exhibit handedness. It's figure of 8. If you look at this end of it, it has a left-hand turn on this end, and if you switch to the other end, it has a right-hand turn on this end. So it's a combination of a left and a right-handed turn. Now if you looked at this in the mirror, this right-handed turn on this end in the mirror would look like a left-handed turn. So it looks left-handed-ish in the mirror, but there's one end's right-handed, one end's left-handed. And there's a statement in mathematics that if you can continuously deform a knot, such as this, into its mirror image, and now the left hand is on this end, then that knot is not chiral and is a symmetrical knot. So this is a well-known symmetrical knot, does not exhibit chirality or handedness. Now, the next symmetrical knot can be tied by pulling this end out, turning that one turn tighter, switching ends, pulling this out, turning this one tighter, putting it back in, and now we have a knot known as the 6-3 knot. It's a 6 crossing knot, 1, 2, 3, 4, 5, 6 crossings, and it is a symmetrical knot. It's the third in a series of 6 crossing knots. There are only 3 6 crossing knots, and this is the only symmetrical one. It's known as the 6-3 knot. Now I'm tying a knot at the end here. We're going to act like this is not a knot. We're going to act like this rope is continuous. so that we have a 6-3 knot here, and we do not have access to the ends of the rope so that we can alter this knot in any way by using the ends. But we can do some things with this knot, which I'm going to show you now. So we take this knot and we make a little adjustment like that, tighten it up, and what we see is that we have a right-handed bowline knot. So if we undo this knot, straighten it out, and we also do this to it, we'll see that we have a left turn here. These are on the left side, and we now have a left-handed bowline knot. So we have continuously deformed a right-handed bowline into a left-handed bowline. And based on that, bowline knots do not exhibit handedness or chirality. Now, they both can be formed from the 6-3 knot. And my proposal is that we rename the 6-3 knot and name it the Bowline Resolution. And if this were called the Bowline Resolution, I think it'd be a lot better than calling it the 6 crossing number 3 knot. So that's my proposal. I'm proposing that bowline knots are not chiral and that they can both be formed from a symmetrical knot and can be continuously deformed into each other and therefore are symmetrical and non-chiral. Thank you.